Hi everybody, my name is Vincent Borgne and welcome to my presentation. I'm the R&D manager at GChem Consultants based out of Quebec, Canada. Acting as the R&D manager, I've had the chance to work on many different types of projects where new technologies were being trialed and rolled out, sometimes for the first time ever. So I hope that today we'll be able to share some insight and some experience regarding the Internet of Things for water monitoring in the mining industry. This is a really broad topic. It covers a lot of things, and today I will not have time to cover nearly everything. I will start by a short introduction. I will then move on to the structure of Internet of Things systems, focusing specifically on instruments and nodes. I will give a few examples from case studies, projects that I've worked on, and I will finish with a few short conclusions. You can read the definition of the Internet of Things right here. Generally speaking, you're probably more familiar with the Internet of Things than you think you are. It's in a lot of industries, it's everywhere. For instance, parking meters. If you have one of those fancy refrigerators with a webcam in it, that would count if you're using Google Home, or if you're using one of the COVID contact tracing apps, and so much more. But the uptake has been slow in our industry, but there's been a real shift in mentality in the past few years for a few reasons. One of them being that these technologies are now more accessible than ever. But unfortunately, 2 years ago, there's been a major disaster in Brazil where a tailings dam collapsed and hundreds of people were killed. And this was really a wake-up call. Mining companies around the world realized the interest in having real-time data remotely at all times from their work sites. Not only to closely monitor the structures, but also to eventually provide real-time alerts for workers or residents. And you can see where the Internet of Things comes in a situation like this, obviously. Another example of where you might want to use this, this is kind of the reverse of the previous situation, meaning that it's a mine in northern Canada where the open pit is below lake bed. So the lake has to be held back with dikes. And to protect your workers, you need to have 100% confidence that your dike is safe. And one of the ways to achieve that is to provide real-time monitoring with Internet of Things enabled instruments. Another example is land reclamation. So this is a drone shot of a project we worked on at GChem. It's a mine that was abandoned some 60 years ago, and the Ministry of Environment in Quebec decided to seal off the tailings and prevent byproducts from leaching into the local water supply. And in addition to all of these works, they added instruments, but the location is really remote and they don't have the staff to send someone every month, drive 6 hours each way just to take a reading. So we put in instruments and all the data is available remotely in real time over the internet. So monitoring has been part of our practices for a long time. We have at GChem separated different levels of monitoring, and starting at level 1 that are manual readings. So you drive out to site, lower your probe, take the reading, take it out, all the way to level 4, where you have internet-enabled loggers and the whole shebang. These have been in use for a long time. Even internet-enabled loggers have been around for decades. The Internet of Things takes this one step further and decentralizes the connectivity and the logging to each instrument or each location, and really opens up a whole new world of possibilities. There's a host of advantages for Internet of Things enabled system. I don't have time to go into a lot of detail here, but keep in mind that if a system is well designed, it should be a lot more hands-off in the end, should be a lot smarter and easier to implement than older technologies. You can split the structure of an IoT system in many different ways. This is how I see it. I'm sure you will find competing definitions on the internet if you bother to look it up. We can speak at length for each of these layers: the instrument, the nodes, the edge devices, the management layer, and the application layer. For today, we're only going to talk about the instrument and the nodes layer. If you have any questions about these or any of the other layers, don't hesitate to reach out to me after this presentation or after this conference. I will be more than happy to oblige. So what are we looking for here at the instruments and node level? We are looking at local memory. Not all products have them, but it's really nice to have. If for whatever reason your gateway goes down, your internet goes down, your radio link is broken, at least your data is saved locally and you can retrieve it at a later date. Wired connectivity is not super common for outdoor applications. As you can guess, you often have very long distances, harsh environments. It's more common in factories or hospitals and whatnot. Instead of that, what we use are radio capabilities. So these are dedicated radios that are very high, that transmit very small amounts of data over very long distances. And they can be sorted in two broad families: star and mesh. And they can also be sorted by range, depending on the exact product, between 1 and 15 kilometers. We want the nodes or the loggers to have multiplexing, meaning that we can connect several instruments to one single logger. This is a great cost-saving measures, especially when you have a thermistor string or 4 piezometers in a single borehole. You want the power requirements to be as low as possible. The technologies we're going to see today have between 1 and 10 years battery life. Some of them need solar panels, but overall, we don't have to run power to the nodes. Programmability is a nice to have, but is usually limited as a way to save on power. You don't want to perform any complex calculations locally. And in some cases, the instrument and the nodes are one and only thing. So that happens, for instance, for tilt meters. It's pretty common. I'm going to show you a couple of brands of such products that we can use. It's not an endorsement of any of them. They're brands I have personal experience with for the most part. So Campbell Scientific is more or less the gold standard. Probably some of you are familiar with this line of products. It's not Internet of Things per se, but it's very flexible and very programmable, and we can make it work more or less like Internet of Things with a bit of effort. You can see on the right, we have thermistor strings coming in at the bottom. At the top, we have satellite modem antenna, and the data is collected and transmitted once a week to engineers located in a warmer climate. Another technology that we use is load sensing. So this is fairly new. They use a LoRa-based radio. It's a new technology that was introduced only 7 years ago, I believe. But it's really taken the mining industry by storm. In this specific case, as you can see on the picture here, you have two piezometers connected to it, and the gateway that connects to the internet is a couple kilometers away. And the battery life in here for this specific application is over 10 years. So it's very much a set and forget. You connect your instruments, configure it, and boom, you have your data available remotely. There are other brands that are more specialized specifically for water monitoring. So for instance, you have In-Situ's ViewLink. Each of the probes and that range of line of products come with a built-in cellular modem. You can see the antenna over there at the top right. So it takes the reading, turns the modem on, transmits the reading, and turns the modem off. So it's fairly power efficient, and it's completely standalone. You have something similar with meter group instruments. So it's really designed to connect specifically meter instruments to the logger, but they have a pretty wide selection of instruments, so it's still fairly flexible. Like the previous product, it has built-in cellular modems and connect directly to the internet. This is a table that kind of summarizes a lot of different technologies. Again, I only have 15 minutes, can't really afford to go into that much detail, but I'll be happy to discuss this with you if you're interested. I want to go over a couple of projects that we worked on at GKM. These projects are actually from a few years ago, but they were some of the first where we actually pushed for these kind of technologies for our clients to use. They're both for tailings in Arctic mines. In both cases, we do geotechnical monitoring, so mostly piezometers, thermistor strings, and TDRs. There are other types of instruments, but it's really those first three that are the most common. As we mentioned before, rough terrain, harsh weather make this very difficult to make traditional instrumentation systems very difficult to deploy. And the ability to collect the data matters at least as much as the instruments themselves. And overall, we're moving, as you can guess, beyond manual data collection. But we had to try out different technologies and make sure we were using the right one for each project. So this is mine one. This is a satellite view. You can see that the site is several kilometers wide. We had two communications tower, one for the southern part and one for the northern part. And a lot of instruments here. We're talking about several hundred instruments in this case. It's, again, a mine that is under a lake bed. We went ahead with Campbell loggers in this case, simply because there were a lot of instruments in any given location. You can see the loggers inside the small shelter. You have the solar panel there, so the system is not only battery powered. And you have the radio antenna at the top that transfers data to the comms tower several miles away. In mine 2, again, this is a satellite view. You have the gateway in a central location, and in this case, we actually did go on site before the project started with both Campbell and load sensing loggers, and we actually tried them out on site to check for the quality of the radio signal and the compatibility with the instruments they had there. And we ended up going with load sensing in this specific case. It was a bit more cost efficient because we were retrofitting existing piezometers and there were only a few piezometers in each location. And we had very long distances to cover, in some cases 5 or 6 kilometers. So this is a typical installation. Again, it feels like we're on the moon. So you have the load sensing node hidden away in this enclosure here to protect it from winter storms. You have piezometers, piezometer cables coming in at the bottom here, and the antenna there that transmits the data automatically to the gateways that are several miles away. So this gives a short overview of what the radio signal quality was. So the node 15, that is pretty far away, has a fairly low signal strength, but still high enough that we get all the readings through. Whereas node 10 is much closer, but we lose over 30% of the readings. And it's hard to tell from the picture here, but there's a big stockpile between node 10 and 9 that blocks the radio signal from the node. So there are a few ways to solve that. We could elevate the node antenna. In this case, we elevated the gateway antenna as much as we could, and we also increased the sampling rate of that specific node so that enough readings go through. You can see here a picture taken from the location of the antenna. It's a really nice site to visit. So 2 Arctic mine sites were compared. Real-time data was required for each. The right data logging technology should be chosen by balancing the following points. Cost, obviously, that's very important. Flexibility, so how many instruments you can connect, types of instruments, if you can program complex behaviors and so on. Power requirements are also important because there is no power out there on the tailings, on the dikes, and exactly how the data would be retrieved and be made available to the right people. So there are different monitoring architectures, star, extended star, bus daisy chains, etc. And if it's something that is new to you, you should seriously consider doing on-site tests before deploying an actual product. You know, these things happen. We have, our client's technician is out there in the cold, in the winter. It doesn't have cellular network, and then the radios don't connect, and there is nothing he can do while he's out there. And it's just a lot of wasted time for everyone. And being able to conduct preliminary studies really, really helps in the end. But it's kind of hard to convince mine owners and mine operators to fork that money over, but in the end, it's usually worth it. So we saw why we could use the Internet of Things and a bit of the how as well. So, real-time data, instrument management, and so on, but there's a lot more that I couldn't cover today. So thank you for your attention. If you have any questions, please don't hesitate. I'll be happy to answer them. Thank you.